This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, your professor for this course, and we're at Lecture 18, the third part of our series on ion implantation. Our reading again is Chapter 5 of our textbook by Campbell. Today we're going to talk about channeling, among a few other topics. Channeling is an extremely important idea in the world of ion implantation, and it comes from the fact that we're not implanting into an amorphous material where the atoms of the solid are randomly positioned. We're implanting into a crystal where the position of every silicon atom is deterministic. It means that there are certain crystal axes, and if the ion happens to be aligned with one of these axes, it can find a channel to move down. So here's a three-dimensional view of a silicon structure, and you'll notice that if I look in just the right spot, there's a long hole that if an ion were to be properly aligned with that hole, you can imagine it could go down that channel for a long ways without being disturbed, versus if it hit at an angle, what it sees at an angle is a big barrier of silicon atoms that would run into them and scatter a lot. So here we display an ion coming in and it's aligned with the channel. Maybe it moves close to a silicon and bounces away, moves close to a silicon, bounces away, but it's essentially like a waveguide guiding an ion, more of an ion guide, guiding the ion through the channel, and it'll go a long ways before it eventually stops. Whereas if that same ion were to come in at an angle, it would bounce all over the place and scatter much the same way it would scatter off an amorphous material without any alignment. This phenomenon we call channeling, and it's a real problem if we let the ions impact onto the wafer normally incident. Here's an example of the kind of dopant distribution that we see with channeling versus no channeling. So without channeling, here in the blue we have a distribution that looks like a Gaussian. Now remember, if I plot a Gaussian on a logarithmic scale, as I've done here, we get a parabola. So we see a parabolic shape, meaning it's a Gaussian. But some percentage of those ions might hit a channel and go further. So here I assumed about 30% of the ions were hitting a channel and going much further, and you can see the range at which it might go is factors of 2 or 4 or 6 longer than the positions of the ions if there's no channeling. So the dopant distribution we get if we happen to hit these channels is dramatically different. Often this is a very bad thing, especially if you're trying to create some shallow junction and the dopants go much farther than we expect them to. So we need a way of getting rid of this channeling effect. How do we reduce channeling? Well, I think the very definition of what channeling is gives us the idea of how to reduce it. We're going to implant an angle. If we are at an angle, we won't hit the channels and the channeling will go away. How big of an angle is required? Well, somebody's worked out some of the physics of this, and if the angle gets large enough, we don't get any channeling. There's some critical angle at which it occurs. That critical angle is given by this formula. We see 9.73 degrees, and then the square root. Here is the Z number, the atomic number of the ion and the target. E is the energy of the ions as they're implanted, as they hit the surface, and D is the atomic spacing, basically how big the channel is in a normally incident, for a normally incident ion. So as long as we're greater than this angle, we won't get channeling. Typically 7 degrees is used because this critical angle is bigger than 7 degrees for essentially all the ions and energies and that we're interested in, with the exception of very low energy boron implants. Sometimes a really low energy boron implant, this won't be a big enough angle, but essentially this is good enough. There's also a little difference between 100 wafers and 111 wafers because they have a different atomic spacing, D. as seen from a normally incident ion. But essentially 7 degrees works, and that has become the industry standard. We use about 7 degrees for all of our ion implantation today. Occasionally we go up to 10 degrees, again, for these low energy boron cases. But doing this angle implantation results in a separate problem that we now have to deal with called shadowing. If we come in at an angle, you know that we've got masks that mask the ions, preventing them from getting into the wafer in certain regions. Here I show a gate stack, and the polysilicon gate, here in the gray, is masking the implantation so that the ions that hit the gate are embedded in the gate. But because of the angle, we get an asymmetric doping profile underneath this gate. And it's just a very simple geometric reason why we get that kind of shadowing. Well, what can we do about shadowing? There's a couple of ways to approach it. One is to say, well, this encroachment of the ions under the gate, that's inevitable, but the asymmetry is not. We'll simply use 2 angles. Instead of just ions coming at one angle, we'll come at both angles, and we'll get the same level of shadowing on both sides instead of just shadowing on one. That's good for lines oriented in one direction. If I include lines oriented perpendicular to this one, then I would need to add 2 more 7-degree angles. So you can imagine left and right and a top and bottom orientation of the 7-degree implants. If we had arbitrary orientation of our features, then we might need to use a whole cone of angles at 7 degrees, or rotate the wafer underneath a stationary 7-degree implant direction. Most of our devices in CMOS manufacturing have only what we call Manhattan geometries. All the lines are oriented up and down or left and right. I mentioned masking. That previous example, the gate acts as a mask to stop the implant from going underneath the gate. That's how we make our source and drain. Selective doping is what we're all about here. We don't want to dope the entire wafer the same way. We want to dope various regions one way. And to do that, we have to mask the implant so that we don't get doping in the regions where we don't want it. As we saw in the last example, the gate can act as a mask for the source drain implants, and thus we call this a self-aligned source drain process. The source and the drain are self-aligned to the gate because the gate itself is acting as the mask. We often use photoresist as an implant mask, and oxide, field oxides in particular, as an implant mask. So for example, in the CMOS source drain implant shown in the figure below, I might be implanting the N-type dopant to create an N-channel device in the P substrate. Well, while I'm doing that, I need to cover the PMOS device with photoresist. So here I show in this kind of orange-brown color, photoresist covering up what will become eventually the PMOS device. So we're not implanting into this device when we're making the source and drain in the N-channel device. And then our field oxide here and here in the pink is blocking in the region where we don't want the source and drain, as well as the gate mask blocking underneath the gate. So in this particular example, there are actually 3 masks being used simultaneously for one implant. Well, how good must these masks be? They have to be thick enough to stop most of the ions from penetrating. Well, they're probably not going to stop all the ions because a Gaussian has a tail that goes on for a long ways. But a general rule of thumb is we want to stop 99.99% of the ions. In other words, we allow 0.01% doping concentration underneath the mask compared to the region where there is no mask. Typically, we modify that rule of thumb according to the designs and the specs of our devices. But this is a pretty typical result. That dictates the thickness of the mask, but also the thickness depends on the mask materials. Higher Z masking materials tend to have better stopping power. They don't need to be as thick. Other materials, photoresist needs to be a little bit thicker. Excuse me. Another issue that we've talked about before is implant damage. We talked last time about Monte Carlo simulators that simulate the trajectory and the position of the ion when it stops. These same simulators can be made to predict the damage done by ion implantation as well. Essentially, though, when a dose gets above a certain level, the result will be amorphous materials. For lower doses, we can have materials that's only partially amorphous. Some of the crystalline structure remains. Also depends on how heavy the ion is. Boron doesn't do as good a job of busting up the crystal structure as, say, antimony does. But, as we know, we've already talked about, we need to regrow the crystal and activate the dopant, and therefore we use an anneal step. If the temperature is too low, or we do it for too short a time, then we don't do a good job of annealing. Annealing is the growing of the crystal up from the seed crystal of the substrate. And what we want is very low levels of defects, crystal defects. We want a perfect single crystal that doesn't change. So we've got point defects and slip defects and loop defects and other ways in which the crystal can be wrong. And to get a low defect crystal, we need typically up to 1,000 degrees, maybe more, and for enough time to get that crystal grown. Unfortunately, high temperature and time results in lots of diffusion of the dopants as well. And if there's too much diffusion, we don't get the junction in the place we want it to be. The best compromise between high temperature and time for low defects and low temperature and time for low diffusion is the use of rapid thermal annealing. And that's going to be the subject of our next lecture. So that gives you a little preview of how we're going to solve this interesting trade-off that we have. Note that ion implantation allows dopant concentrations above the solid solubility limit, especially when we use this rapid thermal annealing, because we never achieve an equilibrium state at these high temperatures. Ion implantation in and of itself is not an equilibrium process, and then if we do a very fast diffusion, we can incorporate the dopants in a supersaturated crystal. All right, that is the end of Lecture 18 and our three-part series on ion implantation. Let's ask ourselves what we've learned. As always, you should be able to quickly answer these questions as we go through them. If you can't, you probably need to review the material some more. So, how and why does channeling occur? What is the most common remedy for channeling? Explain shadowing and what we do to mitigate the problems of shadowing. What is required of an implant mask? And how is implant damage repaired? That's our lecture. Next time, rapid thermal processing.